Okay, so in this video, I'm going to give a bit of an introduction to matching problems. So quite a lot of the course is actually going to be about matching problems. Quite a bit of the time, we're going to be just explicitly developing the theory of matching problems. But also later on, there's going to be a bunch of other problems that are not obviously to do with that theory, but somehow we'll find a kind of cunning way to relate them back to the theory of matching problems and use the theorems that we've proved in that setting to solve some other stuff that looks quite different. So let's just have some examples. I mean, basic example of a matching problem. You've got some set S of students that are applying to university, and there's some set C of university courses, and you want to assign the students to the courses. So in order to do that, I mean, firstly, we need to know what the preferences of the students are and the preferences of the university. So we need to know this set E. E is the set of pairs S, C, where S is a student, C is a course, and your student S is happy to do that course, and also the course is happy to accept the student. Okay, so those are the kind of compatible pairs. Now we want to assign students to courses, so we want to pick a bunch of compatible pairs in a certain way. So at the moment, notice here I've just sort of said student S is happy to do course C. Obviously, in practice, students have preferences. They're sort of barely happy to do one course and really excited to do a different one. We're not actually going to do we're not going to take account of that in the theory we're building here. Of course, there are other theories which you allow for a kind of a range of preferences, but in order to develop those theories, it's good to have done this kind of basic case first, where it's kind of all or nothing. Students and courses are either compatible or they aren't. Another kind of allocation problem. There's lots of kind of allocation problems in computer science. One sort of basic one, you've got some set of tasks you want a computer to do. Maybe you've got some fancy supercomputer with thousands of processors, and you want to allocate the tasks to the processors. That's a kind of matching problem. But the problem we're mostly going to be discussing is like this. I mean, you've got some set P of people and some set J of jobs, and you want to assign the people to the jobs. Okay? So obviously you want to give, you only want to assign people to jobs that they're qualified to do. So we need to know this set E, a set of pairs P, J, where P is a person, J is a job, and the person's qualified to do that job. And the kind of ideal thing is that we want to assign each person. Each person gets one job, each job gets one person, and the person assigned to the job is qualified to do it. So we'll be interested in understanding whether that's actually possible or not. Of course, it's not always possible. I mean, for it to work in that ideal way, then you have to have the same number of people as jobs, which might not happen. But of course, it can also fail to happen for sort of more complicated reasons, like if all your jobs, you've got tons of different specialities in brain surgery, and all your people are only qualified to do rocket science, then obviously it's not going to work out. Okay, so but if it is possible, of course, another question we might be interested in is how many different ways is it possible. We're going to be looking at problems like that in a bit. A traditional example of matching problems is about just assigning romantic partners to people. And so one of the key theorems that we're going to be proving it's called Hall's marriage theorem. It's called that because it was originally formulated in the context of assigning romantic partners, but because we're mostly going to be formulating stuff in terms of assigning people to jobs, but of course it's a key part of the theory that it doesn't really matter the details of what the application is. It's a whole bunch of different problems that are mathematically identical, and we can apply the same mathematical theory in different settings. So what is our mathematical formalism? So we've got two finite sets, A and B. So it could be A could be a set of students, B could be a set of courses, A could be a set of tasks, B could be a set of processors, A could be a set of people, B could be a set of jobs, whatever. And we sort of think about drawing these things in a kind of table. You put the labels from A downwards from top to bottom on the left, and you put the labels from B from left to right across the top. And so a row of that table is a set of the form curly, just a singleton A crossed with B, so that's going across horizontally because the A is labeling how far down you've gone and the B is labeling from left to right. And similarly, a column is a set of the form A cross singleton B for some fixed B. And so partial matching, okay, that's a subset M of E, which contains at most one element from each row and most one element from each column. So, so how should we think about that? Well, just think out to the example of jobs, which is going to be the main example, as I said, that we're thinking about. The idea is that you're going to assign some people some jobs, and these are all supposed to be full-time jobs. So each person is supposed to have at most one job. Okay, so that says that if you look at you've got one row in your table for each person, and you're only supposed to have one job in that row that's been assigned to that person. And similarly, each job only needs one person, so you've got one column in your table for each job, and that's only supposed to have one person in it. So those are the two conditions for partial matchings. Here, this picture is an example of partial of a matching problem. Okay, so I'm not going to say a great deal about this because there's a whole separate video and a whole interactive demonstration that you can use to explore this in much greater detail. We'll just mention a few things here. So we've got our set P of people called Anne, Bob, Kath, Dave, and Ella, or A, B, C, D, E. So they're listed down on the left here. And we've got set J of jobs, librarian, musician, nurse, optician, pilot. Okay, so those are listed across the top here. And then the key piece of data we need is the set E, set of pairs where the person X is qualified for job Y. And this is going to be our E, so particularly we've got, say, this BN here, which says that Bob is qualified to be a nurse. And that's reflected. We've got these three different graphical representations here. There's the BN slot here is white because Bob is qualified to be a nurse. BN slot here has a 1 because Bob is qualified to be a nurse. And then over here, there's a line from B to N because, again, Bob is qualified to be a nurse. And as I say, there's another video and demonstration that goes into this in more detail.